Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been listening to a series of lectures on the subject Electricity and Basic Electronics for the BSc Electronic Sciences degree program. This is the first paper in the first semester of the degree course. This lecture, what we are going to see today, is the 57th lecture in the series. Of late, we have been discussing about the electronics part of the syllabus. We have come to a concept called Boolean algebra and implementation of Boolean expressions into circuits. Before we start today's lecture, let us see the session outline of today's lecture. In this session, we are going to see the importance of negated OR gate and negated AND gate. In the last lecture, I have given some examples for the simplification of a lengthy Boolean expression and also the implementation of the Boolean expressions into digital circuits using logic gates. While implementing, we were forced to use the number of logic gates. Before we could implement any given expression, we need to simplify so that we could reduce the number of gates that are used in the implementation part. All that we have seen to some extent with few examples in the last lecture. While implementing the Boolean expressions, I hope you would have seen two types of Boolean expressions. One is the expression with lots of products which are finally summed up. We call that as sum of products, and the other way of writing Boolean expression is product of sums. These are the two ways of writing the Boolean expressions in general sense. What are these meant for? The sum of products or product of sums, are there any importance attached to it? Today we are going to see all the concepts related to these two types of writing the Boolean expression. For that, the two special types of gates will be very much useful. Actually, when we take the complicated Boolean expressions, simplifying them and then implementing them into circuits is a tedious process. If we depend only on the basic gates like OR, AND, NOT and the other gates like NAND gate and NOR gate, etc., we will have to use lots of gates. But if we could have few more gates which would ease the way of writing the expression and also simplifying the expressions. So, I thought it would be appropriate in this lecture to introduce two other gates, namely negated OR gate and negated AND gate, which are also called bubbled and bubbled OR. Let us see what these gates are. We are going to see the negated OR gate first. What is the meaning of negation? If we take the complement of something, then it is called negation. We normally get the complemented result only at the output stage. In some cases, we can give the complemented term as an input also. In some of the expressions that we have already seen, we have given A as an input, B as an input, and also the complement of A bar and B bar as inputs we have given. So, here the negation, the term represents the complement. What is complemented here? Customarily, the complement is obtained as an output. For NOR gate and NAND gate, if we take, the output is actually complemented. But what about giving the input itself as a complement? So, that is what is called the negated gate. Let us see what is negated OR gate first. This is actually negated AND gate. We have a regular AND gate which will normally give the input which is ANDed. But here we have the two NOT gates connected at the input stage. So, we represent the NOT gate in this manner. So, the input to this AND gate is complemented here. And is it necessary to represent this negated AND gate as the three different gates? But in circuits, we will use a simple symbol for this. The inputs are represented with the bubbles. Here the bubbles represent the inputs are complemented. So, because the inputs are complemented, the bubbles are there at the input stage itself. These gates are called bubbled gates, bubbled input gates or negated gates. It is typically a negated AND gate. What will be its output? The basic operation here is done by this AND gate. So, it will multiply in general sense, it will AND the two inputs given. Here the inputs given are A bar and B bar because of the complemented inputs, and this is perfectly done the AND operation. So, we have a dot here. When we only look at this expression, y is equal to A complement dot B complement or A bar dot B bar, we are reminded of one expression that we have learnt in one of the earlier lectures. What is that? It is nothing but the De Morgan's laws, De Morgan's theorem. Two De Morgan's theorems we have learnt in the one of the previous lectures. So, when we apply the De Morgan's theorem here, we will be able to further modify the output that we obtain here. So, let us see how it is modified. We will have to recall to our mind the De Morgan's theorem. When we use one of the theorems, we will be able to write this A bar dot B bar in another form also. Let us see how it is done. See here, this A bar dot B bar could be easily written as A plus B the whole bar. So, this is nothing but the De Morgan's theorem. When we write this as a De Morgan's expression, we are once again surprised because this is representing nothing but a NOR gate. The output of the bubbled AND gate is having the expression of a NOR gate. So, what is the conclusion here? When we use a bubbled AND gate, the output is nothing but the output of a NOR gate. So, what is the conclusion? A bubbled AND gate is acting as a NOR gate, or in other words, a negated AND gate is acting as a NOR gate. So, instead of using a NOR gate, we can use a negated AND gate also. Customarily, it is called as bubbled gate because the inputs are complemented. The colloquial term for these gates is the bubbled gate. So, bubbled and acts as a NOR gate. So, this has got lots of significance in the Boolean expression simplification. Let us see what is the other bubbled gate. This is negated or bubbled OR gate. Basically, it is a OR gate. The two inputs A and B are negated or complemented and fed as input. So, the expected output is it is A bar plus B bar, because the OR gate will add them Boolean way. If you want to say, it will odd it, the two inputs are odd here. So, it is represented as a single gate in this manner. The negated OR gate or bubbled OR gate will have the inputs bubbled. It is basically a OR gate with the inputs bubbled. And what is the output? As I said, this output is Y is equal to A bar plus B bar. Once again, as it is done in the previous case, this brings to our mind the De Morgan's theorem, one of the De Morgan's theorem. By implementing the De Morgan's theorem, once again we will be able to write this A bar plus B bar as A dot B the whole bar. So, that itself is the De Morgan's theorem, and once again we are able to identify this expression as the expression for the output of NAND gate. Let us have a look at it. This Y is equal to A dot B the whole bar. This is done by using De Morgan's theorem. And what is the conclusion? Instead of using a negated OR, we can even use a NAND gate. So, a negated OR gate is a NAND gate. We can flip the gates as we wish. Depending on the circumstance, depending on the necessity, we will be able to use a bubbled gate and the equivalent of it. Take for example, in this case, a bubbled OR gate is acting as a NAND gate. So, instead of NAND, we can use a bubbled OR instead of bubbled OR, we can use a NAND gate. Why we are learning about the bubbled gate concepts? It is very much useful for circuit implementation. As I said in the beginning of the lecture, there are two ways of writing the Boolean expressions. One is the sum of products and the other one is product of sums. When we write the expressions as any one of these forms, we will be able to implement the expressions using the bubbled gates very effectively. So, let us give a recap of what we have learnt and then go ahead to know more about the circuit implementation part of the two forms of writing Boolean expressions, namely product of sums and sum of products. So, let us quickly have a recap of what we have learnt before we get into the next concept. Let us see what is highlighted here in this two cases. A negated AND gate is a NOR gate. So, this we have to keep in mind, it is a very important result. And the second one is negated OR gate is a NAND gate. These two are the very basic principles of implementing the Boolean expressions into the two forms, namely sum of products and product of sums. But we should always keep the two results which I have reiterated now in our mind, so that it could be easily used for implementing the Boolean expressions. Now, it is time for us to look at the way in which we could write the Boolean expressions in normal sense. So, let us have a look at the Boolean expressions, how it is written. Before we get into the concept of the implementation part, let us have a short break. Welcome back. Now we are going to see the two ways of writing the Boolean expressions, namely sum of products and product of sums. Let us see what we are going to see first. The first thing we are going to see is the product of sums. It is also called as NOR implementation. As I said, the Boolean expressions could be written as product of sums and sum of products. For our first discussion, we are taking the product of sums form. What is product of sums? See, the basic operation here is the two terms are multiplied, or it is a product of two different terms which are given in bracket. But what are given in bracket? They are nothing but the sums. Here we need to keep one point in mind. When we say product, it represents the Boolean AND operation. When we say sum, it is a Boolean OR operation. So, though we call them as product, sum, the Boolean equivalent we should always keep in mind. We should not be confused this algebra with the normal algebra. We are talking about the Boolean algebra in which sum means OR, product means it is AND. That we should always keep in mind. Now, we have first taken up for our discussion the product of sums. Here we have taken two terms only. Let us have the expression once again. See here, these are the two sums, A bar plus B, A plus B, these are the two sums, separate sums, and the two sums are multiplied, or we have taken the product of these two sums. That is why it is called as product of sums. Now, it is time for us to implement this given expression as such without attempting to simplify it. We are going to just implement the given product of sums Boolean expression into a circuit. Let us give a try for the implementation part. Let us have a look at the slide. See here we have the two OR gates, because there are two sums, two plus symbols are here. So, we definitely need two OR gates and the respective inputs are given. The first sum has A bar and plus B bar. So, it is these two are given as inputs. For the second sum, it is A and the B terms are given as the inputs, and the sum is obtained for individual terms, individual sums are obtained. Now, we need one more AND gate to get the product. So, it is also obtained. Because we have seen these kinds of Boolean implementations in the last lecture at length, this has become very easier for us to understand. Now only the real modification starts. So far what we have seen in this part is very simple. Have a look at the expression and draw the equivalent diagram. It is very simple. But now we are going to make modification to this diagram. Let us see what is the modification we are going to make. See, this is a modification. We have introduced the negated operations or complement operations. See, here we have introduced one bubble and here also we have introduced one bubble. What is the meaning of it? If two complements are taken, then the expression does not get altered, and for this input to the AND gate also the two bubbles are introduced. So, one operation is compensated or complemented by the other. We very well know from the Boolean identities that we have learnt, if two complements are simultaneously taken, it remains invariant. It keeps the expression or the term invariant if two complements are simultaneously taken. A bar is A only. So, keep using that concept, we have complemented the intermediate stage twice. So, one complement operation is cancelled by the other complement operation, thus leaving the expression unaltered. Do you agree to that? So, let us have the two circuit once again and see how the output is obtained. There is a slight change I am making. Here the given original expression is just like that implemented. We have 2 OR gates and 1 AND gate. Now, look at this diagram, modified one. We have introduced the bubbles and the intermediate stage is complemented twice. See, these bubbles represent, it is a complement operation and it leaves the final expression invariant. And when we look at the circuit implementation, because of the introduction of the bubbles, set of 2 sets of bubbles, the gates themselves are modified. Is it not? Originally OR gate, 2 OR gates and 1 AND gate were used. Now, after introducing the bubbles, the gates themselves are modified. That point we should notice. So, let us have a look at the diagram once again and understand the change of gate itself. See, originally OR and after the bubbles are introduced, the gate itself is now modified. It is nothing but a NOR gate. This is also a NOR gate. And what about this gate? This gate is nothing but a bubbled AND gate or negated AND gate. So, this is the way we see the negated gate appearing in the implementation stage. Had we not learnt about the bubbled AND gate, we would not have understood what this gate is. So, now it has become easier for us to recognize the gate which is at the output stage as a bubbled AND gate. Again, point strikes our mind, a negated AND gate is nothing but a NOR gate. So, let us see the further modification done to the circuit. So, this is the circuit we have been discussing. This part is going to be modified further because this is the negated AND gate. So, that is going to be the NOR gate. So, now look at the diagram. The final expression is not at all modified, but the gates are fully modified. I hope you could bring it to your mind. When we started the implementation part, we used 2 OR gates and 1 AND gate. But finally, when we end up modifying the expression stage, the circuit stage by stage, all the 3 gates are modified, that too all of them have become NOR gates. So, is it not surprising? Let us have a look at the circuit once again and look at the expressions also. See, the same expression, the same intermediate stages also, and the final expression is also the same, but the gates are totally modified. This gate is a NOR gate, this is a NOR gate, this is a NOR gate. So, finally, we have the NOR gates for implementing the given Boolean expression. If the Boolean expression is in the form of product of sums, then the easier way of representing the expression into a circuit form is by using NOR gates. So, 2 terms we should keep in mind. If it is product of sums form, then it is the NOR implementation. Whenever we come across the product of sums expression in Boolean algebra, immediately the gate that should come to our mind is NOR gate. So, using only NOR gates, we will be comfortably able to implement the circuit. Though the expression suggests the use of OR gate and AND gates, by way of simplification using the Boolean algebra, we need to use only the NOR gates. So, this is a very basic concept, but it will help us a lot in simplifying the Boolean expressions. Now, the second part is also there. We have seen the product of sums. Now, it is time for us to have a look at the sum of products expression. So, let us quickly have a look at the sum of products form also and see how that form is also implemented into Boolean circuit. It is sum of products form. In the first itself, the clue is given, it is going to be NAND implementation. See here, it is called as sum of products because there are 2 products. I have similarly chosen the inputs like A bar, B, A, B, like that, only the operations are different, so that we could easily compare and understand the way in which the implementation works. And here there are two AND operations, A and B. This is A bar and B, A and B, like that. And finally, the sum is taken, so only one OR gate is required. So that is why it is called sum of products. When we have sum of products, it is the final sum of products. It ends with products, sum of. So we need to at least use one sum gate. The sum gate here I mean is the OR gate. So that is what is obtained here. See, have a look at the diagram. There is one OR gate and two AND gates. If we have a very long expression with other variables, then we may have to accordingly use lots of combinational gates here. But I have taken only the two product and one sum expression, so that the concept could be easily understood. Once again, we are going to modify this circuit so that the negated gates are introduced. So what do we have to do? We have to introduce the bubbles in the intermediate stage. Let us see how it is done. See, it is done here. We have introduced the bubbles. Actually, the intermediate steps could be ignored. It is not relevant. It is just retained in the diagram, but they are getting modified. So don't give importance to the intermediate step. Give importance only to the introduced bubbles. So once the bubbles are introduced, one complement operation will cancel the other complement operation. So it keeps the output invariant. And see, the gates are modified. AND has become NAND now. The OR has become the negated OR or the bubbled OR. It has become easier for us to recognize this bubbled OR as the NAND once again. That is what we have learnt in the previous case. Before the break, we learnt about the negated gates. So it has become easier for us to recognize the bubbled OR gate as NAND gate. So finally, what is the conclusion? The expression, if it is in the form of sum of products, then we need to use the NAND gates for implementation. I hope you could have understood how the sum of products and product of sums forms are implemented using the NAND and NOR gates respectively. In the forthcoming lecture, we will see other combinational gates also. We have just for example taken A and B as the inputs, but there are other gates also available. We can have more than 2 inputs. We can have 3 input gates, 4 input gates, and multiple input gates we can have. So in the forthcoming lecture, we will be able to take up those gates also for our discussion. It's time for us to look at summary of today's lecture. In this session, we have seen the importance of negated OR and negated AND gate, and also we have seen the product of sums and sum of products way of writing Boolean expression. Let's quickly test our understanding by answering this question. Implement the following Boolean expression using either NOR or NAND circuits. So we have to identify whether it is written in sum of product of sums, and accordingly we have to choose the gates and implement them into circuits. So see you in the next class with multiple input gates and other concepts for simplifying Boolean expression. Thank you for watching.